Good morning. I'm from Munich, and I hope that you not only think of the Oktoberfest and the Bayern Munich, the famous soccer team, but we also have two universities, the LMU, Ludwig Maximilian University, and the Technical University, and I'm at the Technical University. And I'm chair of physical chemistry, and we are interested in small clusters, and mainly in their chemical properties. And so we are looking at small clusters in the gas phase, in an ion trap, and we are looking at kinetics of these species. But we are also interested in thermal catalysis. We are putting these clusters on the surface in a size-selected way, and then we are interested on the size-dependent properties. But we also work on photocatalysis. This is another topic of today, and a little bit of electrocatalysis. This I will not talk about. If you would like to understand these chemical properties on these small clusters on surfaces, you also have to have techniques, spectroscopic techniques, and we are using a bunch of spectroscopic techniques, XPS, UPS. We also have SHG, second harmonic generation, and we use this technology mainly in order to get information on the chirality of these clusters. Here we use circular dichroism. I will not talk about this topic today. But then we also have STM, local probes, with which we try to understand the dynamics of these clusters on surfaces, because it's important. If you have a chemical reaction, you have a thermal, you have a temperature, given temperature, and you have to know if these clusters are stable or not. And so the aim is to somehow develop concepts in the UHV at controlled conditions, and we would like to apply them on normal conditions. That means we're also working at ambient pressures, but also in the liquid to see whether these concepts are valid in these environments. Then two other groups of our institute, they are now tenure tracks, they are former postdocs. They are working at ambient pressure, increased pressure, but also quantum sensing. Now, why clusters? I was studying in Bern, and my PhD supervisor was Ernst Schumacher, and he's probably the father of cluster science. In fact, he was director of Ilford. This is a company that produces photo paper, and he realized that very small silver particles somehow have unique properties because they were responsible for the latent image. And this was a motivation when he came to the University of Bern to study these small clusters. And this is a picture I saw during my studies, and you see the electronic structure of atoms with the highest occupied molecular or atomic orbital and the lowest the LUMO. And then, of course, on the other side, you see the bulk with the band structure. And you see, for instance, the HOMO-LUMO gap in the atom, which is substantial and which is, of course, also important for the chemical properties for redox reactions and also for thermal reactions. On the other hand, on the bulk, this HOMO-LUMO gap doesn't exist. And so his idea was that in between there has to be something, and he started to produce molecules of sodium, dimers, trimers, tetramers, and so on. And of course, his thinking was that these small particles, they have unique electronic structures, and he wanted to somehow employ these to tune chemical properties. And this was kind of the motivation also for me. Today, of course, we have a little bit a different view. We have atoms, we have clusters, here clusters in the non-scalable size regime. I will explain you what I mean with this. And then we have nanoparticles, larger particles in the scalable size regime, and then, of course, they are going to the bulk. Now, that means we are kind of exploring the third dimension of the periodic table, because we have now another tuning parameter to change the chemical properties, not only the periodic table, but the size. And so we call this the third dimension of the periodic table. There are other words, small is different. This is very known from Musi Landmann. This was his saying. And in our first papers, we stated every atom counts, because we can tune these chemical properties atom by atom.
Because of the health issue. But Uzi was supposed to come.
Okay, that's a pity that he's not here. Okay, now let's have a look at an observable. You see here the size, you have an observable, and you see that if you are in a small size range, these properties, they deviate or they change very strongly as a function of size. And then, if you go to larger sizes, the properties are scalable. What does it mean? That means we can use scaling laws in order to describe their properties. We have, for instance, the properties as a function of r, radius, or the number of particles, and they can be explained by the property of the bulk. And then we have a radius-dependent term or a term dependent on the number of n. Here, alpha is 1 or 1/3. And there are examples that you can apply these laws. For instance, the ionization potential of potassium. You see here the scaling law as a function of r and as a function of n. But there are also melting temperatures you can express by these functions. What we learn by this, that these properties in the scalable size regime, they very smoothly change as a function of size. We don't have these drastic size effects. And so if you have here the ionization potential of a bunch of metal clusters as a function of 1 divided by r, you see indeed this linear behavior. And if you go to smaller sizes, of course, you have these variations. But there's another aspect of this scalable size regime. Here you see also a rather old mass spec, and you see that we have somehow numbers where we have a decrease in the intensity of the mass spectrometry. And the authors of this paper, they explain this by so-called geometric shells. That means if you look at these numbers, you see that we have stable clusters at closed geometric shells if we apply Mackay icosahedra. And so we can also define a periodic table as a function of size. We simply fill the shells of these Mackay icosahedra along the period. And then, of course, along the group, we have these closed shells. Of course, it's a little bit more complicated. It is the Wolff's theorem, the Wolff shape. But what is important here is that we have facets which are very similar to single crystals. That means we have a particle surface analogy in this scalable, non-scalable size regime. That means if you learn properties from single crystals, we can apply them to these nanoparticles. Of course, we have a different ratio of these facets. We also have borders of these facets which will be relevant for a catalytic reaction. For instance, if you have a diffusion, you have a hindered diffusion along these rims. And so if we try to somehow characterize or summarize some concepts, guiding principle of this scalable size regime, we can say that we have a smooth variation of these physical and intrinsic physical and chemical properties as a function of size. So we expect also not very drastic changes in the catalytic properties. But of course, we have a strong surface to bulk ratio. And so if we see in comparison to bulk increased reactivity, it is mainly due to surface to bulk ratio. Then, of course, as I explained you, we have different facets. With a given reactivity, we have this Wolff construction, which can influence these diffusion barriers. And of course, on the surface, we have different coordination numbers, which can influence the catalytic properties. But there are also properties that are dependent on the particle support interaction, because in heterogeneous catalysis, you put these particles on a surface. And so you have a modification at the interface which can influence the catalytic properties. You can also have a lattice mismatch with the underlying support, and you can change a little bit the structure of these particles, but this will not be very drastic. And then, of course, you also have spillover and reverse spillovers. Particles, intermediates on the particles can diffuse on the surface and do a reaction on the surface, or just the opposite. But now let's have a look at the non-scalable size regime. These are also very old measurements, ionization potential of sodium, and you see these very drastic effects. And you certainly know that we have these magic numbers. But here, the magic numbers are not structural, but they are the electronic structure. We have closed shells. And perhaps you know that we can explain this with simple models like the Cellium models where you can explain this molecular structure. That means also here we can design a periodic table on this non-scalable size regime. But here it's the electronic structure. That means we can have closed shells, we can have open shells, and from this you can imagine that we have distinct, very different chemical properties. But there are other important facts in this non-scalable size regime. As I mentioned before, we have a HOMO-LUMO gap. We have different ionization potential and electron affinities, very different to the bulk. And this is, of course, important for the catalysis because often these particles are on a support material and you can have a charge transfer to the cluster or from the cluster to the bulk. That means you change the electronic structure. If you have a bulk particle, it doesn't matter if you add a simple charge. But here, on these very small clusters, you change the electronic structure. That means you can tune the catalytic properties not only by size, but also by the interaction with the support. But there are other facts which are relevant in this non-scalable size regimes. We have different structures. And this is calculations by Uzi Landmann, and he observed that gold is planar, nothing to do with bulk. That means this will also influence the catalytic properties. But even more, in these very small clusters, and one of the very important properties is that you have different isomers, and they can be very close lying. That means at finite temperature, you always have a Boltzmann distribution of these different structures. And each isomer can have a different chemical property. And so you have to be aware that you talk about size effects, it can also be simply a question of an isomer. And they can interconvert it into each other at temperatures, and this we talk about dynamic structural fluctuality, because along a reaction, they can change the structure. And we believe that this is a key for the low temperature catalysis we observe for these very small clusters. So there are also some concepts that can guide us through catalysis with these small clusters. We have these distinct size-dependent electronic structures. We can also have new intermetallic phases, which does not exist in bulk materials. We have strong impurity effects. That means you can dope, for instance, a gold cluster with cesium, and you can charge the gold score. This changes the reactivity, for instance, for the oxidation of CO. Then we can have these unique structures. We have this fluctuality. They are fluctual during chemical reaction. And we can charge the cluster. We can change the oxidation state. And this will, of course, very drastically change the chemical properties. But also here, we have dynamic properties, which are very important. I told you about these isomers, the structural fluctuality. That means we have to consider this. And then last but not least, of course, also here we have an interaction with the support material. That means we have this oxidation state we can change. We can change the structure upon interaction with the support materials. And also, of course, we can also have this spillover and reverse spillover. So you see that these guiding principles are quite different. Here we expect very drastic effects. And what I would like to do is show you 3 examples. First of all, single atom catalysis, a special case of cluster catalysis. Then I will talk a little bit about dynamics of clusters on surfaces, and then I will talk about photocatalysis. If you would like to study single atoms, as the word tells you, you have to study single atoms. And this you can, of course, do only in the gas phase. And our experimental setup is shown here. We have a laser vaporization source, we have ion optics, we have a quadrupole mass spectrometer with which we can select a single size, and then we can put these clusters in an ion trap where we can do chemical reactions. We can heat and cool down this ion trap so we can get information on kinetics. And then the products, after a given time, we can analyze with a time-of-flight mass spectrometer. And I show you One example here, the sub-characteristics of the cluster source. We can produce clusters up to about 100 atoms. We can store these in this ion trap up to 10 seconds. We can change the pressure. And of course, we can then analyze these with a time-of-flight mass spectrometer. Now you see here single tantalum atoms interacting with methane. And what you see if you look at the mass spec is that you can absorb or interact with the first methane molecule and you have a dehydrogenation. That means you are producing hydrogen and you have a CH2 species adsorbed on the tantalum cluster. You can have a second one of these CH2 species, a third one, a fourth one. And then you have molecular adsorption. And so you have a distinct reactivity of these tantalum atoms which are positively charged. Of course, you can do this as a function of size. And you see the tantalum dimer. We have a second CH2, and then nothing happens anymore at these experimental conditions. Tantalum 3, we have 1 CH2. Tantalum 4, again 1, 2, and then we have molecular adsorbed methane. Then if you go to the 5, it is inert. That means you see this very strong size dependency of the chemical reaction. And we can also measure rate constants of the first step. Here for atom, dimer, trimer, tetramer, and you see that indeed the atom is specific. It has the highest rate constant for this very first step, the adsorption and reaction for production of CH2. And then, of course, the molecular adsorption is changing as a function of size. And so you have a distinct chemical properties of these tantalum clusters. Green, you have this dehydrogenation, have a low reactivity, and these are completely inert. Then you can modify these tantalum clusters. You can oxidize them, and they are getting reactive. But I don't want to talk about this. I would more focus on these tantalum atoms. So this is a summary. You see that in the equilibrium, the products of the atom, dimer, trimer, and tetramer, and this is a calculated structure of usilanmand. You see even a CC coupling. Of course, this we didn't observe in the experiment. Single atom catalysis, of course, these are not in the gas phase. They are on surfaces. And so they don't like to be singles. They have to interact. They try to produce clusters and so on. And one of the very first experiments on these size-selected clusters was with single atoms. And these single atoms of rhodium, palladium, and silver. And so the motivation for this work was that it has been shown on single crystals that you can have a cyclotrimerization. You have C2H2, and it can produce benzene. And in the surface science studies, it has been speculated that you need an ensemble of 7 palladium atoms in order that this reaction takes place. So this was our motivation to study the size dependency of this cyclotrimerization, expecting that we need a critical size. But we were let's have a closer look at this reaction. Of course, we have the CH2. We can have a decomposition. We can produce H2, and we can poison the catalyst. We can produce ethylene hydrogenation. We can have a polymerization. And here we see the cyclotrimerization. If we combine 3 of these molecules to form benzene, this intermediate can again have a hydrogenation to produce butadiene, or we can have hydrogenation to produce protein. You see, this is a very complicated process. It has a lot of reaction paths that can take place. And indeed, this has been observed on single crystals, different materials, that you have a different, quite a complicated product spectrum. But on clusters, you see that even a single palladium atom is active. A dimer, trimer is active. And they are very selective. We only observed benzene. If you go to larger clusters, of course, you have different reaction paths that is open. But of course, here are now the reactions of different atoms. You see silver on magnesium oxide, a very tiny reactivity. You have palladium on magnesium oxide. You have here a reaction at 220 K at low temperature. Here you have thin films. I will show you that the thin film has the influence that it charges the palladium, and this will be important. If you use a thick film, you change the reaction temperature. So the environment of these palladium atoms are important. Rhodium, you see production at 430 K. Now the question is, are these indeed single atoms? Because we go up to a given temperature. Therefore, we studied with simple experiments IR. We used a probe molecule CO, and we're looking at as a function of temperature of the vibrational frequency. And on palladium atoms, you see a typical on-top vibrational frequency of CO at low temperature. Then you can heat up the sample. You change a little bit the shape, you have a different coupling of the CO molecules, which gives the shape, but you have still a characteristic for an on-top bound CO molecule. And then if you go to larger temperatures, above 300 K, you suddenly observe a bridge-bonded CO. That means you have to have two palladium atoms in the neighborhood so that you have a bridge-bonded CO. That means at this temperature, they will diffuse. And of course, if you heat up, you produce larger clusters. So the dynamics is extremely important if you talk about single atom catalysis, because you have to know what you have on the surface. We did similar experiments on rhodium and silver. And for rhodium, we observed that they are stabilized also at step sites of this magnesium oxide. But then at 300 K, they go to F centers, oxygen vacancies. And then at 400 K, they are migrating. Silver, they are not stable. Already at 200 K, they form larger clusters. As I told you, there is another aspect of this single atom catalysis, and this is the chemical environment. And Gianfranco Pacchioni, he observed that if you would like to have this cyclotrimerization, you can use, of course, a neutral palladium atom. And you can absorb first molecule, a second. You can make this intermediate, this pentacycle, but you cannot absorb a third molecule. This is, of course, necessary to have the cyclotrimerization. But if you charge the cluster, you can absorb it and you can make the cyclotrimerization. That means the charging is also relevant for the reaction to take place. And this is the reaction path, also quite old results. And you see here that you have the rate determining step is indeed the formation of benzene. But you have to charge the cluster. That means you have to absorb it on an electron donating site. This is a F center. Or you can produce very thin films so that you have a charge transfer from the underlying support material. So you can tune the chemical reactivity. For rhodium atoms, they are stable at these edge sites. And there is a steric hindrance for the reaction to take place. That means single rhodium atoms will not be active. And silver atoms neither, because we have a powder repulsions and we cannot absorb this molecule. So if you interpret these reactivities, you have to know the dynamics and you have to know the chemical environment. This is very important if you talk about single atom catalysis. On silver, this very tiny peak, it's certainly not from atoms. We produce clusters. Palladium, we have strong evidence that it is indeed these single atoms. On the rhodium, of course, at the temperature of 430 K, we produce clusters. That means this is the reactivity of clusters and not of single atoms. And this dynamic behavior is also observed in real catalysis. This results from the Grunwald group in Karlsruhe, and he showed that for the oxidation of CO on platinum on ceria, you have a dynamic change of the formation of atoms and clusters. If you are at oxygen-rich conditions, you are producing single atoms. If you are at CO-rich conditions, you are producing clusters. And he attributed the chemical reactivity of the CO oxidation to clusters and not to single atoms. And this is a very important behavior. So we learned that the dynamics of these clusters are important to somehow interpret the chemical properties. And in the next example, I would like to show you the dynamics of platinum clusters on a magnetite iron oxide surface. That means we have an iron oxide surface. There are some important properties of this iron oxide, and one of these important properties is that the stoichiometry, the surface stoichiometry, remains constant. That means if you are at oxidizing conditions, the iron 3+, they are diffusing into the bulk to keep the stoichiometry constant at the surface. If you are at reducing conditions, it's iron 2+, which is diffusing into the bulk so that the stoichiometry remains constant. You also have a dynamics. You have iron atoms that can diffuse on the surface, and if you have hydrogen, you can also have diffusion of hydrogen on the surface. But this is not our interest. We use these support materials as a support of size-selected clusters. And we're depositing platinum clusters on these surfaces, and our interest was in the dynamics.
What is the video?
This is the iron plus. You see other videos. These are iron plus atoms that are moving on the surface, and here you see hydrogen atoms on the surface.
STM?
STM, yes. So, yeah. It is fast STM. This is one of our specialty. We have a fast STM. We also have atom tracking. I will show you some videos later. And so we are interested in what can happen on the surface, these platinum clusters. Are they stable? Do we have encapsulation? Do we have Ostwald ripening? Do you have Smoluchowski ripening? Smoluchowski ripening is the clusters itself. They move on the surface, they coalesce, and they produce larger clusters. These are the questions we were asking. And so we were depositing these clusters, platinum 5, platinum 10, platinum 19, on this iron oxide. And you see here height measurements of platinum 5, rather sharp distribution of heights. It's between 1 and 2 layers. Then we have platinum 10, twice the number of atoms. We are in between 2 and 3 layers. And we have platinum 19, we have 3 to 4 layers. And you see here the size distribution of these clusters, and you see that they are rather identical. That means we are producing these size-selected clusters on surfaces, and we can monitor them by STM images. Now what I would like to show you is that by using different techniques, TPD, we use XPS, but we also use STM, that we will see that the clusters are stable at given temperatures, and then we have a reverse spillover of oxygen onto the cluster. And then if we increase the temperature even further, we have an encapsulation. That means we form a very tiny iron oxide over these platinum clusters. And then only at this stage, they start to migrate. We have Smoluchowski ripening, and at the later state, we have Ostwald ripening. Here you see as a function of temperature, the cluster coverage for these 3 sizes. You see that the cluster coverage of platinum 5 is stable up to about 400, 450 K. And then you see a decrease of the cluster density. That means something happens. On the platinum 10, you see that they are stable a little bit to higher temperatures, and then we also have this decrease in coverage. That means there is a ripening going on. And for the largest clusters, here showing in red, it is stable up to rather high temperatures, 700, 750 K, and then you see the decrease in the coverage. Now let's have a look, a closer look as a function of temperature. And one thing you can do, you can absorb CO. And then you can, as a function of temperature, to measure the desorbing CO. It's a simple TPD, temperature per gram desorption. And you see here the desorption from platinum-19 and platinum-5. And you see a different chemical behavior, as you expect, because we have a different electronic structure. But you see something surprising. Without putting oxygen into the chamber, we observe CO2. That means we produce CO2 on the surface. That means we have to have oxygen on the cluster. That means that this happens, we have to have a reverse spillover of surface oxygen onto the cluster. Of course, this reaction can now take place at the rim, at the interface of these clusters to the oxide material, or on the surface. But if you normalize the reactivity, you see that it scales with the number of surface atoms. So we are confident that the reaction takes place on the surface. That means we have indeed a reverse spillover onto the cluster. This has also been calculated by Gianfranco Pacchioni. Activation energy for this migration is about 1 electron volt. This is also confirmed by these height measurements. You see here for platinum 19 at room temperature the original data. And then you see if we heat up, the distribution remains constant. That means we have the same clusters, but the height is decreased. And also calculations by Gianfranco Pacchioni showed you that if you put oxygen on these clusters, they are flattening. Of course, you also have another electronic structure, so you have another STM image. And so this flattening is also another indication that we have this reverse spillover in this temperature range. Then we go higher in temperature. Here you see a clean iron oxide surface. We have very little CO adsorption, no CO2 oxidation. We then again deposit these clusters on the surface. This is the results I showed you with the CO desorption, CO2 formation. But if you now heat up to 800 K, go down, and again dose CO, you have a different behavior. You see here now CO desorbing in this broad feature, and this is typical for iron oxide. And most important, you don't see any CO2. That means we speculate now that the cluster is covered with magnesium oxide. We can again deposit clusters on the surface, do the same experiment, and we see an additional feature of this CO from iron oxide. That means this is indeed related to the clusters we have on the surface. It scales with the cluster. We can also see this STM images. You see here a cluster, and you see that it etches away iron oxide in the environment, which is used to cover the cluster with this thin film of iron oxide. But you can also use XPS, and you see here XPS of platinum, the surface sensitive peak and the bulk sensitive peak, and you see indeed that we have a decrease of the feature of platinum in the temperature range where we observe this SMSI, this encapsulation. The bulk sensitive peak does not change. That means the cluster do not diffuse into the bulk. But we can also look at the iron oxide, and you see a very small feature here. And if you take the different spectra, you see indeed that we have a feature growing in, which is typical for iron oxide, iron 2+, at the expense of iron 3+. This is another indication that we have this very thin film over these clusters. That means we have now in the next step this encapsulation. And now let's have a look what happens later. We heat up again, remember, these clusters are now encapsulated with a iron oxide film. And then if you heat further up, you see that you change the density of the clusters. You have ripening. That means if you change the density, it means that they migrate on the surface, they coalesce, you have Smoluchowski ripening, you have larger clusters, and you decrease the cluster density. This is also shown by the high cluster height distribution. As a function of temperature, you see a broadening of the peak. That means you have the initial state, which are encapsulated platinum 5, platinum 10, and if you go to higher temperature, you have double the size. That means you produce larger clusters. You have this Smoluchowski ripening. And then if you go in further, you see that the coverage remains, but you have a very broad cluster distribution or size distribution. Now you have Oswald ripening. That means you grow larger cluster at the expense of smaller clusters. You see even very small clusters which are disappearing and forming large clusters. So we have a rather good picture of what happens with a cluster on the surface when you are heating up. They are stable. We have a reverse spillover, we have an encapsulation, and then we have the formation of larger clusters. Now the question is, can you observe this in real time? And here we have fast ASTM studies. And you see here, indeed, these are measurements at 630K, an encapsulated platinum cluster, which is diffusing on the bulk in real time. And you also see here the formation of this iron oxide, etching away the neighborhood of the iron oxide of these clusters. You are producing now these thin films. We can also observe the Smoluchowski ripening shown here. And you see that these clusters migrate, they form larger clusters. And so we can also observe this, what we deduce from other experimental setup. Now the question is, can we follow a cluster? Can we use an ASTM tip and follow the cluster during its diffusion? And for this, we developed these atom tracking methods with which we can do this. And you see here a platinum 5 of an iron oxide. And then we start to track this cluster. And you see that it migrates along the row. These are the resistance times of this cluster on the surface. And interestingly, if we now put the iron oxide lattice on this, you see that it does not discriminate these iron vacancies. The resistance times is always the same. If you look a little bit longer, we can also observe that these clusters can migrate over the rows of this iron. And you see here the motion of this iron 5 on this surface. So they are really dynamic, and this is something you have to consider when doing catalysis.
These are real time.
This is real time. That means it has very dynamic structure, and if you work at high temperature, you have to deal with these kind of phenomena.
There are some preference sites, some preference that you stay there for longer.
Yes, there are some preference, of course, and then they hop to the other, and they hop to the other.
Is it a Levite flight?
No, I don't think so. No. There are, as we have other experiments on graphene. There we think that it is connected to this, but here no.
Is there any standard deviation?
Pardon?
Is there any standard deviation in this measurement? Like, have you tested the standard deviation in this measurement?
Lateral and horizontal distribution in length.
This motion.
If we have
This motion, have you measured the standard deviation? Like, have you repeated the experiment?
no, this we didn't measure. Yeah. Okay, that means we have a dynamic system, and if you heat up, then we form stable clusters, square shapes, platinum 5, platinum 10, platinum 19. We start with, of course, the number of atoms of 5 are 4 times lower than platinum 19, and you also see a lower density. That means at one point you make stable structures, which may be inert or chemically reactive. That means I hope I could convince you that these clusters are dynamic, that we can have different processes. On iron oxide, we have these processes I described to you, but this is unique for iron oxide. If, for instance, on Syria, we have another dynamics. Here, we don't have this encapsulation, but we have a flattening of the cluster as a function of temperature. So we have to somehow really study the system as a whole. It can vary. Now the last topic, I would like to talk about photocatalysis. Here the dynamics, of course, is a little bit less pronounced because you can work at ambient temperature, at room temperature. And so what I will talk about is the oxidation of alcohol reforming on these systems. And this is, of course, relevant for renewable hydrogen from methanol or ethanol. It can also have highly relevant products in perfume industry, benzaldehyde, and so on. But there is also in organic chemistry, remember that, for instance, tertiary alcohols cannot be easily oxidized. And the question is, can we use photocatalysis to selectively oxidize these tertiary alcohols? We are interested in the fundamentals of this photocatalysis. That means we would like to study the mechanisms how this reaction takes place. So there are different ways, many ways to do photocatalysis. Homogeneous molecular photocatalysis. You have a liquid, you can have a plasmonic particles, you can have another photocatalyst where you excite, and then in this excited state you induce a photocatalytic reaction. You can have plasmonic photocatalysis where you excite the plasmons, you heat up the system, and probably this heat is then used to steer a chemical reaction, or we can heterogeneous photocatalysis, and this is what we are looking at. That means in our system we have a semiconductor, in this case it's a titanium dioxide, which is responsible, or there is the light harvester. And then we have a co-catalyst, and these are our platinum clusters. The role we have to determine what happens on these clusters. And so on the semiconductor, you can of course tune, you can dope these semiconductor materials, you can change the band gap, you can somehow influence the positions of the lower and upper edge of the conduction and covalent band. So you have tuning parameters to change the optical properties of these semiconductors. On the co-catalysts, we are in the non-scalable size regime. We have quantized electronic structure, and so we expect that we have different behavior on this species. And so our samples are consisting of a titanium oxide surface, and then we have these size-selected clusters on this surface. Also important is that also on this titanium, we have so-called BBO sites. These are bridge-bonded oxygen vacancies. That means you have an oxygen vacancy. We'll see that this will be relevant. And so we are trying to study these photocatalytic reactions on these systems. Again, you see here the setup. We have a laser vaporization source, go too fast, with which we are producing these clusters. Then we have the ion optics, a quadrupole mass spectrometer, and then we can deposit these clusters on a titanium single crystal, which we can heat, and then we can, of course, deposit different sizes of these platinum clusters. And last but not least, we have an OPO laser with which we can stimulate a photocatalytic reaction. And so what we are measuring, we are preparing these samples, we have clusters, we expose it to ethanol, methanol, then we turn on the laser, And in the first experiment, we simply use the products that are formed on these photocatalytic systems. If you talk about photocatalysis, 99% of the interpretation is lying on this picture here. It's kind of an electrochemical picture. That means you have your semiconductor, you have your valence band, the upper edge of the valence band, you have the conduction band, lower edge of the conduction band. And in this picture, the redox potential oxidation and reduction has to lie in between the band gap. That means you have the oxidation, the lower edge of the band gap, and you have the reduction at the upper edge of the band gap. That means you have restrictions on the semiconductor. You have to choose the band gap, or you have to align the band gap with the redox potential. And this gives you some limitations. And of course, our initial idea was that by tuning the cluster size, we can tune the electronic structure. We can tune somehow the states here in this range here. And our hope was that we can tune in this way the catalytic reaction. But it turned out that this mechanism will not explain our results. And I will show you results which suggest that we have a different behavior of this photocatalytic process. And here is a cycle we propose. We have our titanium oxide surface, we have these BBO sites. And in the first step, the methanol is reacting with these BBO sites, and you are producing a methoxy or alkoxy. And then, if you shine in light, you produce holes, and these holes oxidize this methoxy and form aldehyde. And then this aldehyde has to thermally desorb from this reactive site. Then, of course, you have, upon adsorption, you produce a first hydrogen on the surface. The oxidation produces a second hydrogen on the surface. And we showed that you have now a migration of this hydrogen to the cluster, and you have a thermal recombination of hydrogen on the cluster, and you're producing H2. That means we only need one photon. It is not in line with this picture where we would use 2 photons. Now, let's have a look, and we use different methods in order to somehow nail down these mechanisms. We have defect engineering, isotopic exchange experiments, kinetic isotope effects, co-catalyst engineering, changing the catalysts, and photonicity. Now let's have a look at our results. You have here titanium without clusters, and we expose this to methanol, and you see, and then you illuminate this sample with photons. And you see that, you see a little amount at the very beginning of formaldehyde, almost no hydrogen. Then we stop the light, we turn on the light again, and you see nothing. That means we poison the surface. We have an initial amount of formaldehyde that is formed, but then the catalyst is dead. Now we can put clusters, co-catalysts on the surface, and the picture completely changes. You see now steady formation of formaldehyde as long as we shine light on the photocatalyst, and we also see hydrogen that is produced. You turn off the light, you see an immediate decrease of the formaldehyde, and we have a thermal tail of the hydrogen. That means we need platinum. This is what we learned. We need platinum in order to produce hydrogen. Then we can also compare the formaldehyde formation, the kinetics, on a clean surface and on a platinum-covered surface. And you see that the kinetics of this formaldehyde formation is very similar. That means the formaldehyde is really not formed in the neighborhood of platinum. It's on a single site, on these BBO sites. Then we can also increase the photon flux. And you see here at the very beginning, kind of linear behavior, first order behavior, and then it saturates. That means we only need one photon. And then, of course, we can also look at the kinetics in the dark. That means we can look at this behavior here, and I will discuss in the following what we can learn from this. But most important, you see that the decrease of formaldehyde is decreasing as soon as we turn off the laser. That means the charge carrier dynamics seems not to play a role. This is also something in photocatalysis. People often think that the charge dynamics is important. Here the kinetics is much more important than the charge carrier dynamics. And we can also do this at low temperature. That means we can somehow suppress the thermal processes, then we can heat up. And you see that the hydrogen is indeed formed in a thermal process. And then last but not least, of course, if you have a platinum crystal, it is undoped. That means we have a band bending that is upwards. That means if we shine light on this semiconductor, the minority species, which are the holes, go to the surface. The electrons go into the bulk. That means we have only holes on the surface. That means we need not these electrons for the reduction. It's a thermal process. So this is also an indication that this is really a photo and thermal process. Now let's have a closer look. We have seen that these BBO sites are important. And so you can tune these BBO sites on our titanium single crystal. So you can produce single crystals with a high number of BBO sites and a low number. And this you can titrate by water. And you see here two surfaces, a different amount of BBO sites. We estimated about 14% and here about 1.6%. Now you see the influence of the photoreactivity. And you see that if you have a high density of BBO sites, you have a high reactivity because you have more reactive sites. If you decrease the BBO sites, you have here a lower reactivity. That means the BBO sites are indeed relevant for this photocatalytic process. And you can measure the reactivity as a function of the density of BBO sites, and you see a linear behavior. It's a quasi-first order process. That means this dissociative absorption of methanol is the rate determining step. This is the key, that you absorb this on these BBO sites, you make the methoxy or the alkoxy. So this is a very important step. That means, here again shown here, this is the rate determining steps. And then we need the holes to oxidize this to the aldehyde. Now, what other steps can be important? We see that also the mobility of the hydrogen to the cluster can be important. And for this, we studied different isotopologues. That means you hear the reactivity of methanol with only hydrogen, and here with deuterium. And you see a decrease in the reactivity if you use the deuterated methanol. That means this diffusion of hydrogen will also be relevant in determining the reactivity of this oxidation. And you can also use other isotopologues, CH3OD. And here you see that you have a statistic formation of D2, H2, and HD. That means you have a same concentration of these species at steady state around the cluster because you have this statistical distribution. On the other hand, if you use this isotopologue, you see here CD3OH, you have another reaction channel going on. You now have an exchange of the OH and you are producing CD3OD. This may indicate that the diffusion of D is lower on the surface. It has time to have this isotopic exchange and produce this isotope. Of course, we can try to quantify this. And for this, we can use the kinetic isotope effect. It means it is the reaction rate of methanol divided by the reaction rate of your other species. And if you look now at our mechanism, you have first the adsorption of your alcohol and the formation of the methoxy. This kinetic effect has been measured. It is about 1.3. Then we have, of course, the photo formation of the aldehyde. Here we don't expect a large isotopic effect because we have a lot of photon energy, and so the small differences in 0-point energy of the different isotopes are negligible. And so we don't expect. We even expect the negative because we have another reaction channel taking place. Then we have, of course, the diffusion. Here we have a larger isotope effect. Then for the recombination of hydrogen, again we have a small kinetic isotope effect. This has been measured on single crystals. And here are our results. And you see indeed that we have the highest isotope effect for CD3OD. That means it is indeed this diffusion of the hydrogen is relevant in this process. If you look at the other isotope, you see that the CD3 and OD, the CD3 has a much lower kinetic isotope effect. This is consistent with this picture here, because this is formed by the photo process. We have a lot of photon energy. It doesn't matter because we don't have this. The differences are negligible. And here, for the rate determining step, of course, we have a small isotope effect. In these two cases, of course, we also have the other reaction channels that are opening, these back reactions. And here, as I showed you, this CD-OH exchange. So these measurements show you that not only the adsorption of the alcohol and the methoxy is important in this process, but also this diffusion of hydrogen to the cluster. And this is also confirmed when we are changing the cluster density, because if you are changing the cluster densities, if you go to low densities, then you increase the distance between the clusters. You increase the diffusion length, and we have a higher kinetic isotope effect. This is another indication that this diffusion is indeed relevant. This is again summarized in this slide. Now we can look at different cluster sizes. We can tune the number of atoms. And you see indeed, if you have the same coverage, atoms, we have platinum 5, platinum 10, and then platinum larger than about 50 atoms. And we see here a maximum of platinum 10. That means we have small size effects, but they are not determining. These size effects are also observed in the kinetics. If we have here the platinum 10, and here we have the platinum 5, we have the same number of atoms. Here we have less clusters on the surface, we have a larger distance, but we still have a higher rate constant. That means we can conclude that these platinum 10 are indeed intrinsically more reactive. Then, of course, you can also increase the cluster coverage. Of course, you have more platinum. You produce more hydrogen, but you also decrease the diffusion length. And so we have a higher reactivity. This is true for platinum 5. We see this increase. For platinum 10, it seems to saturate the given coverage. Platinum, we would like to replace by nickel. Nickel is known as a very good hydrogenation catalyst, but we see that it is poisoning. That means if you do the reaction, the reactivity is decreasing as a function of time. That means in this case, we have another reaction taking place on the nickel. The nickel absorbs methanol, and then it is known that it produces CO and H2. We also showed in our very first experiment on side-select clusters that small nickel clusters can dissociate CO. That means you produce a carbon layer on the nickel and you're poisoning your recombination catalyst. Therefore, it is cheap, but it's not working. This has also been observed by Auger spectroscopy, where we see a clear evidence that we produce this carbon layer on these nickel clusters. That means you have, of course, to be, it is important that you somehow design your co-catalyst so that it is not poisoning. I hope I could convince you that by different experiments that we have this catalytic cycle of this photoreaction. That means we have the adsorption, dissociative adsorption of the methanol on this PBO site. We have a photo-driven process. This is the formation of aldehyde. Then we have the migration of hydrogen to the platinum clusters. This is a thermal effect. And then we have the desorption of this hydrogen. So it is a very defined mechanism. One step is missing. Where is the electron? Because if you have an electron-hole pair, the hole will be produced for the oxidation. The electron is in the bulk. But of course, we changed the PBO site. And so during illumination, the electron migrates into the bulk, the hole goes to the surface. It makes the oxidation, but if the aldehyde desorbs, we have a deficiency of electrons, and it is refilled by the electrons that we produced in this photo excitation. That means the cycle is indeed closed. Now, why is this important? We have shown that this mechanism I introduced in the very beginning has some restrictions on the semiconductors. That means you have a band gap. You see here for different semiconductors with different band gaps, covalent band, conduction band, the upper edge and the lower edge. And I told you that you have to design the band gap in such a way that the oxidation potentials lie in between the band gap. So there are very strong restrictions on the use of the semiconductors, because you not only have to align the oxidation potential, but also the reduction potential. For the alcohol oxidation, this is shown here. This is the oxidation, and here we have the reduction potential. And so titanium wouldn't work, for instance, for the alcohol oxidation. You need other oxide materials. But our mechanism showed that the conduction band is not relevant because we don't have this reaction. We have a thermal process. We have a recombination of this hydrogen. That means in our case, we only have to tune the lower edge of the upper edge of the valence band. And of course, we have to tune the chemistry on the surface. This is more relevant than this electronic structure of the semiconductor. And though this opens new materials space to design photocatalysts. Now can you ask the question, is this a general mechanism? Can we apply this for other alcohols? And indeed, we did study many alcohols. This methanol, ethanol, and then we have here this species and here. And you see that for all these primary and secondary alcohols, we have exactly the same mechanism. We always adsorb the alcohol in this methoxy. We have the formation of aldehyde, and then we have the thermal production of hydrogen in a very selective way. There are cases, of course, we are producing radicals on the surface. And if you have a defined temperature windows, these radicals can combine. And so there are some alcohols with this product of the CC coupling, for instance, here or here. But we can also understand this with our mechanism, because we have these radicals on the surface which are producing with our mechanism. They are migrating, CC coupling, and they are dissolving on the surface. But it is not the main product, and it's very dependent on the temperature. That means we can also use the temperature to tune kind of the selectivity. Now the question is tertiary alcohols. I showed you that in our mechanism, in the aldehyde formation, we always split the CH bond in alpha position. In tertiary alcohols, we don't have a H in the alpha position. What happens? And here you see the results of butanol, and you see that again we can explain the results with our mechanism. You see the acetone formation, but here you don't produce any hydrogen, but you produce the radical CH3 that we detected with mass spectrometry. That means again we have exactly the same mechanism that we proposed. At low temperature, you also have the photoactivated thermal reaction and producing isobutene. But the main product is exactly according to our mechanism. Other tertiary alcohol, butanol, here. This is 3-methadol, 3-hexanol. Here we now have different hydrocarbon chains. And the question is whether we have a selectivity. And what you observe that in this case, we didn't see any methane or CH3 radicals, but we make the splitting in the other position here or here. And we are producing pentanone and butanone. Again, with a very defined selectivity. It is independent of the pressure, it is independent of the temperature, it is simply related to this photostimulation, the oxidation of the reaction with the whole of this methoxy species, and we produce this in a very defined, with a very defined reactivity. So we can apply, I showed you, I hope I could show you that we have a new mechanism, and if you use at primary and secondary alcohols, we have a alpha H abstraction. If we have a butanol, we have this radical ejection, and if we have general tertiary alcohols, we have a selectivity, we split these hydrocarbon chains, and probably the selectivity is steered by the stability of these radicals, ethyl or propyl radicals. And so we can kind of tune also here the selectivity. So this is a summary of this part. I showed you that the photoreaction mechanism is different from the photoelectrochemical pictures. We have a hole-mediated oxidation at BBO sites and a catalytic hydrogen recombination at the platinum sites. I hope I could show you that the conduction band is thus not important because we don't have a reduction. And I also showed you that we can even oxidize tertiary alcohols in a very selective way. Last but not least, what I didn't show you, we also performed these experiments at ambient pressures and in the liquid phase. And for methanol, we see a very similar product spectrum. That means we believe that also here, this mechanism can be applied. Thank you for your attention. I hope I could show you a little bit single atom catalysis, that you have to be careful, that dynamics is important, and I could also show you how you can interpret photocatalysis of this heterogeneous photocatalyst. Thank you for your attention.
Thanks for this dynamic talk, same like the clusters. So I have a couple of questions. First one, when you mention about the reactivity of the tantalum species,
yes,
with different number of atoms, can we intuitively predict that what are the factors, what is the factor, or what are the factors, or is it a complex interplay of electronic and geometric factors to determine the reactivity?
I mean, Uzi did some calculations on this methane activation on tantalum clusters, and he suggests that it is somehow the electron fluctuality of these in these clusters which are determining the activation of the methane. It's an electronic effect and less a structural effect. This is what the calculation, what the suggestion of Silangman is.
More towards the electronic.
Exactly, yes.
Second one is about this Smoluchowski ripening.
Yes.
So is it only Brownian motion control, whether there is a factor of the element or the number of atoms which are there in the cluster? Is it only the Brownian control?
No, it is determined by the interaction. I mean, we also showed on other substrates, if the area of interaction is large, you have a stable cluster. And so the smaller cluster where you have let's say a small contact zone, the mobility is much higher. And so it's strongly dependent on the support material. And also, I mean, if you have a weak interaction with the substrate, you have the preference of a Smoluchowski ripening. If you have a strong interaction with the substrate, you have Ostwald ripening. And so you can tune also this ripening by the interaction of the cluster support. And so for instance, on graphene, it is only a Smoluchowski ripening because you have such a weak interaction. On magnesium oxide, you have a lot of Ostwald ripening because of a strong interaction with the substrate, and then of course the atoms are stabilized on the surface, and then they migrate, and then you have this Ostwald ripening. So it is really dependent on the cluster support interaction.
But Ostwald ripening also depends on the curvature, right? So for the Smoluchowski ripening, whether it also depends on the curvature?
Yes, it's a source of free energy in the classical way.
So in single atom catalysis, you was talking about this selectivity of where you are showing the acetylene polymerization. There is a formation of butene, butadiene, and you said that it is very selective for the benzene formation. So
yes.
What exactly driving the selectivity?
This is a. I think these are steric effects, but this I do not know. I cannot give you a. There are no calculations, and we don't know the mechanisms driving this reaction. But I think in the atom it's steric effects, that you have this high selectivity for benzene, and then if you have a larger clusters, of course you need hydrogen, and then of course you have a larger surface, and then you can have this hydrogenation reaction.
Size of the cluster, that is not the factor.
Pardon?
Size of the cluster.
Yes, it is an important factor. I mean, there can be electronic effects, but I do not know because we didn't calculation. But let's say a naive picture is the surface area. I mean, if you have for the atoms, we see that we have a very high selectivity for benzene. And I believe these are steric effects because you have not a space to absorb hydrogen, for instance, to somehow hydrogenate the intermediate. If you have a large clusters, of course you have a different electronic structure, but how it influences, I don't know. But you certainly have additional absorption sites of hydrogen, and then you can hydrogenate the intermediates, and then of course you can steer the reactivity, the selectivity.
Then we might get different.
With different size, you change the selectivity, but let's say the guiding principles, it's complicated. Yeah. I mean, also the charging plays a very important role, because for instance, on palladium, we have seen that you have to have a negative charge to absorb additional molecules, and so you can tune also with the charge the selectivity. For instance, if you have positively charged and you cannot absorb enough molecules, you can hydrogenate the intermediates, and so you can tune the selectivity. But to formulate general guiding principles, it's of course you have to investigate every case.
Also, one more, this in the photocatalysis, this hydrogen diffusion is there. So in case of methanol, the rate is more, and in case of the deuterated one, the rate is more. So is it because of the size or what? Means the diffusion rate that depends on the size or?
At the diffusion rate, I mean, the rate itself is constant. For hydrogen, of course, you have a constant, each step rate constant, but it's, of course, the diffusion length. And so if you change the density of the cluster, if you have at low density, you have a higher diffusion length. And so you have, of course, the deuterium is lower because you have the 0 point energy. I mean, you have the 0 point energy of the OH bond is more stabilized, so the activation energy is larger. So you have a slower motion of the deuterium. This is, yeah.
Thank you.
So what you should all know is that if you ask more questions, your chances of going to heaven will increase. Okay, and as a result, I will give you an extra second. Other questions?
I was fascinated by your discussion of how to make hydrogen from methanol, and I wondered what happens if the methanol is wet, that you have water
Okay,
along
then
with the methanol.
this is a very important point. That because I mean, if it is so selective only at water-free and oxygen-free conditions, because then you have different channels. Then you can start to oxidize, you can produce CO, for instance. And so it is very critical that it is really water-free and oxygen-free. It's a very important point.
Yeah, in this example of the diffusion of platinum cluster that you showed on the iron oxide.
Yeah.
So what's the typical frequency at which this cluster shuttle between the?
Oh, this I have to look in the. I cannot by heart.
So I was just wondering, is it slow enough that you can also capture the dynamics of the product formation in your desorption?
No, I don't think so.
Otherwise,
No,
is
I
it
think
too
it
fast?
is too fast.
Oh,
It's too fast. Yes,
Okay.
it's much faster. Yeah.
You have a question? Otherwise, I have one. Okay.
Continue
No,
our
but
interest.
students have to get certificates. That is why.
So we are running late. That's why they can ask in the detail.
You said that oxygen diffusion, right? In second portion that you talked about, oxygen mobile. Oxygen is.
The reverse spillover of oxygen. Yes.
And is it oxide? And why I'm asking this question is that you said charge on the surface is important in aggregation, the cluster mobility.
Mm-hmm.
So is this whether it is oxygen or oxide, does it decide the fate of the cluster?
We don't know. I mean, when we show two XPS of this state to answer this question, we don't have the results, and so we don't know.
Now, when you talked about tantalum
Mm-hmm.
or any of these cluster systems when they are reacting,
Yep.
I use this when you use a term adduct. I don't know what term you used. Used absorption. You say this is absorbing. Now the product of methane.
Methane, it is dissociatively absorbing on the surface.
Yeah.
That means what we know is that you have a carbon, we have two hydrogen, but we do not know this, how it is on the surface because we have only mass spectrometry.
Yeah.
We did some IR studies at Felix in synchrotron, and we could show that we have a distribution of CH and the H and the CH2. This is from spectroscopic measurements.
Thank you, sir, for revealing the interesting chemistry that unfold when cluster meets the surfaces. Thank you.
Okay.